In this video, we're going to talk about some of the basics of probability and also what probability has to do with statistics. So to start, what is a probability? In mathematics, probability is any number between 0 and 1 that's sort of a measure of or that describes how likely an event is to happen. So as you may already be aware, going from 0 to 1, a probability of 0 represents an event that cannot happen. This would be impossible. Whereas a probability of 1 would be completely the opposite. So a probability of 1 means that the event must happen or it's guaranteed. So it's fairly unusual to actually get probabilities of 0 and 1 because those would not be very interesting events. But typically we'll get a number somewhere in the middle. So a probability of 1/2, for example, maybe if we were flipping a coin, right, there's a probability of 1/2 that you get heads, probability of 1/2 that you get tails. We can also have probabilities represented by percentages, so we might hear a 20% probability of rain, for example, and these are just matching up to their corresponding fractions, so 20 out of 100, or in this case, 1/5. So quick basic example, if we're flipping a coin, the probability of getting heads on the coin, since this is 50-50, this would be 1/2, exactly in the middle. The probability of getting heads or tails on the coin, well, if you flip a coin, you have to get either heads or tails. There aren't any other options. So the probability of this is 1. We're guaranteed to get one or the other of these possibilities. Thirdly here, if we flip a coin and observe the result, the probability that we see 7 would be 0 because this is just not one of the possible outcomes. We're not talking about something where 7 is a possible result. When we're talking about probabilities in this fashion, a useful thing to think about is what's called the sample space. So the sample space is basically a list of all the possible outcomes to an experiment or a scenario. So for example, if we're flipping coins, this is a typical probability experiment, right? We don't know what the result's going to be. The sample space would be all the possible outcomes from, in this case, flipping 3 coins. So if we're flipping a coin 3 times, we could have all 3 heads, for example. If we don't have all 3 heads, that means we have some number of tails. It's a good idea to practice listing these things out for this probability section. So for example, if we have 2 heads and 1 tail, that tails could be in any of 3 positions. So it could be last, it could be right in the middle, or it could be first. So these are the 3 possibilities that have 2 heads and 1 tail. So we've got 3 heads, 2 heads. The next option would be just 1 head with 2 tails. And again, that 1 heads could be in any of 3 positions. So tails, heads, tails, or tails, tails, heads. So again, these 3 all represent 1 heads and 2 tails. And then finally, if we reduce the number of heads again, we just get all 3 tails, and we've only got 1 possibility for that. So this is the sample space for flipping 3 coins. You'll notice we have 8 possible outcomes in this sample space. And we can use the sample space to help us find the probability of different events. So another little definition here, an event in probability is a collection of outcomes. Now the outcomes were sort of what the possible results could be from the experiment. So with this flipping heads and tails, these were all, each one of these is an outcome, one possibility. An event can be a combination of these. So for example, we could have the event, and these are typically represented with uppercase letters like a capital A. So our event A is the event that at least 2 heads come up. Now there's several different outcomes where that would happen. We could have 2 heads and a tail. We could have 3 heads, for example, since that's at least 2. And again, we had some other possibilities for having 2 heads. So if we went through the sample space, we could list out all the different outcomes that fall into this category. So this is a single event that happens to have 4 different outcomes as part of it. Here's another event. B is the event that we get all tails. Now, if we're still talking about flipping 3 coins, the only way that can happen is if we get tails, tails, tails. So this would be an event that's just a single outcome. We would also call this a simple event, sort of meaning that there's only one way for this to happen. So in these situations where all the outcomes are equally likely, we can compute the probability fairly easily. I'm using this probability notation here, right? The probability of some event A is the number of ways that A can happen out of the total number of outcomes. So for example, in this event A that we looked at here, there were 4 ways that A could happen, right? 4 outcomes where there were at least 2 heads out of a total of 8. We had 8 events in the sample space. One thing to be really aware of here is that these events have to be equally likely. When you flip a coin, having heads, heads, heads versus heads, heads, tails, those are equally likely events. And that's not always the case in probabilities. So for example, if we're talking about weather, we might have some outcomes where it was raining, or it was sunny, or it was snowing. These are all different outcomes, but they don't have the same probability, or at least in most cases they wouldn't. So this is mostly useful for sort of theoretical probabilities where we have controlled probability. For example, if we draw a card from a standard deck of cards. So if we're dealing cards for a game or something like that, the probability of drawing a diamond card, we can interpret this as saying, well, how many different ways could we draw a diamond out of how many total possibilities are there, or how many total outcomes? So if we're picking a card from a standard deck, there's 52 possible outcomes, right? There's 52 different cards that we could get. Now, how many of these are diamonds? We'd have to count up all the diamonds, right? We have ace, 2, 3, 4, etc. of diamonds. There's 13 cards that would be diamonds. So this would represent our probability, 13 out of 52. And of course, this ends up being 1 out of 4. Another way we could get to this, of course, is that this is 1 possible suit out of 4 possible suits. And the suits are also equally likely, so we could interpret it that way as well. Again, here, if we want the probability that we draw an ace, we can do the same thing, right? How many different ways can we draw an ace? Well, there's 4 different aces, so there's 4 possibilities there out of a total of 52 possibilities. Or if we reduce this fraction, this would be 1 out of 13. Another example using this process, we're rolling 2 dice. These are standard 6-sided dice. The first thing I want to find is the probability that we get doubles. Now, one way we can do these problems is to first write out the sample space, right? We want to know in this case how many ways can you get doubles out of the total number of possible outcomes. So you might be able to do this in your head, but if you need a little bit of organization, we can start listing out the possibilities for rolling 2 dice. So these are 6-sided die, meaning that each one can have the numbers 1 through 6. So we could have 1 and 1. We could have 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. Or we could have 2 on the first die, 1 on the second, 2 and 2, 2 and 3, 2 and 4, and so on. So we keep listing these out in this nice systematic fashion. I'm going to make a grid here, and we can use this to help us solve the problem. So we see we get this sort of grid here. Now we were looking for the probability of getting doubles, so we can go through and pick out all the doubles, double 1s, double 2s, 3s, 4s, 5s, and 6s. Well, those are all the doubles, which means that there's 6 possibilities out of a total of, well, there's 6 rows and 6 columns here, so there's a total of 36 possibilities. So for the probability of doubles, we would say 6 doubles out of a total number of 36, or in this case, this reduces to 1/6. Similarly, if we want the probability of getting a total of 5 on our dice, we can use this sample space again. So we look at all the possibilities and say, okay, how many of these have a total of 5? So these guys are all too low. We could have a 4 and a 1. We could have a 3 and a 2, 2 and a 3, or a 1 and a 4. These are all the ones that would add up to 5. So this is 4 possibilities, again out of a total of 36, or 1/9 would be our probability. So the probability of getting a total of 5 when you roll the dice is 1/9. Again, we can always interpret probabilities as percentages, and sometimes that's helpful to figure out exactly what this means. So 1/9 is about 0.111 repeating, or about 11.1%. So this means a little more than 10% chance of getting a total of 5. Related to this process of having equally likely outcomes is what's called empirical probabilities. And this is going to be a lot more useful in the statistics side of things, since, of course, we're not usually doing statistics on things like flipping coins or rolling dice. So the idea of an empirical probability is that we've got some amount of data about some things that have already been observed. In this case, we've got a flu vaccine that was given to 100 people, and then we have information about what kinds of side effects those people got. So either no side effects, mild side effects, or severe side effects. And our question asks, if you get the vaccine, what's the probability of having severe side effects? Well, we can work this out just the same way. Using our historical data, how many people got severe side effects out of how many total? So there were 3 people that got severe side effects out of a total of 100, and this gives us our probability, 3 out of 100, or 0.03, right? This would be 3% probability. To go along with this, I want to find the probability that you would have any side effects. So same thing, right? Our total is still 100, but we want to know, well, how many of those 100 people had any side effects at all? Well, 72 had no side effects, so we don't want to include those. We had 25 with mild side effects, and then the 3 that had severe. So that would come out to 28. So 28 out of 100, or if we wrote this as a decimal, this would be 0.28, or 28%. Another empirical probability problem. So in this case, we have our data sort of organized into a table. And this is going to be fairly common when you have a lot of different categories. It's really helpful to organize it into a table like this. So in this case, we've got some categories of income, and then we also have some categories of how long these people spent shopping each week. So because we have categories in 2 different types, we can make this grid. So for example, 208 people made between 40,000 and 60,000 and shopped between 3 and 9 hours a week. When you make these tables, it's a good idea to make totals for each row and each column. So we can see, for example, the total of people who shop between 0 and 2 hours is broken into the 3 income levels, but it's added all the way up at the bottom here into 544. So this problem asks, what's the probability that any person that we select shops more than 10 hours each week? So we say, okay, how many people shopped more than 10 hours each week? So we look at our 10 plus hours column. Now we do have this broken down into income level, but in this particular problem, we don't care what the income level was. We just want to look at the total number of people with that much shopping. So that was 480 people out of the total of everything, which you can see is added up down here. If you're making one of these tables themselves, if you total each row and then total each column, the total of these 3 numbers along the bottom should be 1,600, and the total of these 3 numbers along the side should also be 1,600. That's one way to check and make sure you haven't miscalculated anything. So our probability is 480 out of 1,600, or if we reduce this, this is a 0.3 or 30%. Aside from computing probabilities directly like we just have been, another important thing that we'll use quite a bit in these calculations is the idea of a complement. And this is not the same as giving someone some nice piece of information. A complement in math is sort of the opposite of whatever we're talking about. So for example, if we know that the probability of rain on the 4th of July is 1/4, what is the probability that it won't rain on the 4th of July? So this is a pretty basic one. If the probability of rain on the 4th of July is 1/4, we could think of that as 1 out of 4 days on the 4th of July it would rain. Well, that means that 3 out of 4 days it would not rain. And in general, we're following this rule here. So the probability of no rain, this is the complement, and the notation here is the same letter representing our event with a bar across the top. That means complement. So the probability of no rain is equal to 1 minus the probability of rain. So we're computing basically the probability of the opposite happening. If we know the probability of rain is in this case 1/4, then the probability of not rain is 1 minus that, or 3/4. So this complement is not A. Another example, 3 out of every 1,000 parts on an assembly line have defects. If you select a part at random, what's the probability that it's good? So we're looking for the probability that a part is good. And we're not given that probability, but the probability of it being good is the opposite of it being bad. So we can use this complement rule to say probability of a good part is 1 minus the probability that the part has defects or isn't good. So the probability of it having defects, well, they tell us that 3 out of a total of 1,000 parts have defects. So this would be our probability of a bad part. And then we just do the subtraction. Now you have a couple options. You can do this as fractions and find a common denominator. So if we find a common denominator of 1,000, this ends up being 997 out of 1,000. Or if we convert this, this would be 0.997. The alternative is to just convert to decimals right away. This would be 1 minus 0.003, which still comes out to 0.997. So again, if we think of this as a percentage, this is 99.7%, or in other words, we have fairly close to 100% chance that the part will be good. The other thing I want to talk about in this video is sort of why we care about probability when we're talking about statistics. And this relates to what's called the rare event rule in statistics, or what we mean by saying something is unlikely. So to see what this is really talking about, I have a little sort of fictional scenario here. We've got a study done on a drug that's supposed to prevent heart disease. So half of the participants are given the drug, half are given a placebo, and the people who took the drug, 4% of them developed heart disease after 10 years. The people who took the placebo, 17% had heart disease. Now this next calculation is not something we're going to be doing here, but we will talk about how to find this kind of probability later on. If we assume that the drug has no effect at all, so it's just as good as the placebo, the probability of getting these results is about 0.00026, or if we think of this as a percentage, right, this is 0.026%. Is the drug effective? Well, 0.026% is very, very small. We would say that it's very unlikely that we would get these results if the drug indeed had no effect. Now, unlikely does not mean impossible. It's very possible, well, it is possible that the drug really doesn't have any effect, but we just got lucky here. But because this probability is so low, statistically speaking, we would assume that this drug has to have some kind of effect on heart disease. The people who took the drug have a significantly lower rate of heart disease than the people who took the placebo. And this probability has a lot to do with how many people we have in the sample, and sort of the differences in the percentages and all of that. So there's a lot that goes into it. But the rare event rule is basically saying that when you have something with very small probability, in statistics we typically assume that that didn't really happen, that there's something wrong with our assumptions. So in statistics we like to use two different words. This first is unlikely. So unlikely is just basically saying that there's a low percent chance that this will happen. In this class, the guideline is going to be 5%. If the probability is less than 5%, we consider that unlikely. If it's more than 5%, we could call it likely or just not unlikely. This is very similar to the phrase unusual that we talked about before, but these are slightly different. For example, if we were talking about heights, if you have height 5 foot 7 inches, this is both unusual because that's much higher or much taller than most people, and unlikely because a very small percentage of people have a height this tall. Similarly, if we have a bank account balance that's exactly $475.61, say, this is could be considered an unlikely bank account balance because, this is a very specific number. The chances of you having exactly this much in your bank account are probably quite small, although we'd have to actually look at the data. There are a lot of bank accounts out there. So this is probably unlikely just because it's unlikely that you would have this by chance. But it's not unusual. This isn't a particularly high or a particularly low bank account balance, at least depending upon your perspective. So this might be unlikely but would not be considered unusual. So just to summarize, when we're talking about unlikely events here, we want to think about this study example. When we see something that has a very low probability, we're typically going to assume that that result is false. You can think about it as if your friend flipped a coin 10 times and they got 9 heads in those 10 flips, you might suspect that this coin isn't really fair. It's not a 50-50 coin. Now it might be that you just got really lucky, but the probability of getting 9 heads in 10 flips is fairly low. Especially if we then said, flip the coin 100 times, and we got, say, 97 heads. Even though this is a possible outcome, its probability is so small that it would lead us to think that there's probably something wrong with the coin, or that, maybe we're observing the heads incorrectly. And this is the idea of the rare event rule for statistics, and we'll use this reasoning when we talk about sort of statistically significant results. To finish up, here's a couple questions for you to try. The first question is just a probability calculation. List out the sample space for the genders of 3 children in a family, so boys and girls. So if you have 3 children, you could have, for example, a boy, and then a boy, and then a girl. That would be one possibility. Then, assuming that each gender is equally likely, find the probability that there are 2 boys and 1 girl in the family. So you'll use the sample space for that. And then here's sort of an interpretation question to go along with this. Suppose a family has 10 children and 9 of them are girls. The probability of this happening with boys and girls being equally likely is about 0.00977, and we'll look at how to compute that in a later section. Would we, as statisticians, say that there's reason to believe that for this family, girls are more likely than boys? Right, so think about what we would conclude based on that. That's all for this video. See you next time.